For my project, I've decided to create a multi-class classifier for Gen 1 Pokemon. What this means is that I'll need to train my data to be able to distinguish between other Pokemon. For simplicity reasons, I'm going to assume that when I'm testing an image to determine what Pokemon the image represents, that the image will always be that of a Pokemon, and not of something random. I will be using MATLAB to help me pre-process images, train my data, and then eventually test the classifier. Or in other words, what we're trying to figure out is,
who's that Pokemon?
the majority of my time spent on this project has been used to create a database that will be utilized for both training and testing my algorithm. Originally, while creating my database, I named each image the name of the Pokemon it represented. Doing this ensured that during the training stage of the algorithm, I would easily be able to extract the name of the Pokemon. As you can tell though, the database became very messy, especially since the image had multiple different angles of the Pokemon embedded into one image. The original format for the images I downloaded online contained borders and 4 images in one. To make running the algorithm more simple, I decided to clean up my database using MATLAB. First, if the name of the image did not exist as a folder, I would create it. Then, I would splice the image in 4 in such a way that the borders would no longer show. While doing this, I also resized all the images to 512 by 512 and named the images 0, 1, 2, and 3 and placed them in their respective folders.
Now that our database is set up, I focus on pre-processing the images. The first task is to focus the image on the Pokemon. Once this is done, the image is then resized to 512 by 512. One of my friends, Chin Lee, designed a program that allows a user to rotate, shift, and zoom in and out of the image. This custom-built tool saved me a lot of time, as I could quickly adjust the images. Now that the image is focused on the Pokemon, I apply a Gaussian blur using the transition matrix located to the top right of the screen. The blur assists in removing noise from the image, such that only significant edges are present. As a result, Sobel's kernel also becomes more effective. Sobel's kernel scans the image vertically and horizontally to find significant changes in pixel intensity. The higher the variance, the brighter the output. Applying a threshold forces any variance below the threshold to 0. Since we have both pixel intensity change horizontally and vertically, I create a new image whose pixels are the arctangent of the kernels. This new image represents the angle between the horizontal and vertical edge detection Sobel kernels. For each of the training images, we create a circle of the same size as the previously mentioned custom-built tool. Within this circle, we overlay as many boxes as possible. The box size is user-defined. Using the image containing the angle between the edges, as shown on the left, we take the mean of all the pixels in a box and store that value within a feature vector. I also store the folder name, which is a classifier label, into an additional cell within the vector. Doing this will make checking whether our answer is correct or not much easier later on. Once all training images have been converted to a feature vector, we combine them all to form one big feature vector table. Now that we have a trained database, all that's left is implementing the 1NN algorithm. The first step is to perform the same actions executed on the training images to the testing image, except for adding the classifier label. Then I replicate this feature vector until it's the same size as the training feature vector table. At this point, we now sum the training and testing feature databases and keep the smallest value and its label. To make the angle of the testing image rotationally invariant, I take the original image and rotate it at a user-defined amount of degrees and perform the same actions listed above. There are several difficulties that were encountered throughout this project. The primary issue being that the majority of the training images were pictures of figurines, and the testing images are all drawing-like. The figurines also only capture one specific position of the Pokemon. Some even had minor scratches and engravings. There are also several variables that are user-defined. Therefore, finding the most effective value is very challenging. The last complication I ran into is validating that I implemented the algorithm correctly, as error in classification is expected. Here's a quick demo of how my project works. At the beginning of the code, all the user-defined variables are declared. The main for loop goes through all the training images and stores it in a feature vector table. All of these images that you see are the training images after the pre-processing phase. This takes a while though, so I'm going to go ahead and jump to the testing. Now that our feature vector table is complete, I'm going to run the testing file. The algorithm takes a bit of time to run because it classifies the same image for every 20 degrees that the image can rotate. Ideally, I'd like to use 5 degrees, but that would make the algorithm 4 times as slow. Overall, a fair portion of the predictions are logical. There are still a few that are humorous though. Potential ways to achieve a better result include using clear images during the training phase, increasing the database size and incorporating different positions, altering some user-defined variables such as a blur parameters and threshold for Sobel's kernel, and changing the number of feature columns extracted.